We all experience the world differently, and as strongly as that positively aids in our diversity, it also means that we don't all start at the same step. Some of us are born with perfect health, which puts them somewhere ahead, while some of us are born with genetic disabilities that hold them back.
In reality, it doesn't matter where hearing loss originates from. What matters is the people it alienates. As of 2023, 432 million adults and 34 million children suffer from hearing difficulties around the world.
A study made by the World Health Organization in February of the same year predicted that by the year 2050, the number of people with hearing difficulties will reach 700 million people. 1 in every 10 people will have a hearing deficiency.
The inability to hear and the subsequent inability to speak and successfully communicate makes it much harder for a deaf person to form human connections with the people around them. And even though we are fortunate to live in a world where the social stigmas surrounding deafness are no longer a major problem, the isolation a deaf person can experience on a daily basis requires them to work extra on battling the possible mental health issues as well as cross over the gap between them and the rest of society.
And in an era of continual technological growth, our project combines wearable technology, 3D printing, and multiple AI fields to help seamlessly integrate the deaf into their societies.
Our project is composed of two main parts. The first part is responsible for converting sign language into spoken Arabic. A deaf person signs while wearing the glove. Upon changing the bending of the fingers and the orientation of the hand, the used sensors send specific values to the Raspberry Pi for processing. The processed data is then sent to a neural network model that predicts the signed letter. This letter is then sent to a text-to-speech algorithm that sends the audio equivalent of the letter out on a speaker. The glove can also be used to append complete words through strings of letters. The hardware used for this segment can be categorized into 1. Sensors, 2. Processing unit, and 3. Actuators. The sensors used on the glove are flex sensors to measure the bending value of each finger, an accelerometer MPU 6050 to calculate the orientation of the hand in the X, Y, and Z axes, and two touch sensors that are placed in specific positions on the glove to distinguish between similar characters. The input data from the flex sensors go through an analog to digital converter MCP3008 before it enters the processing unit. The pre-processing and processing operations on the input data are performed using a Raspberry Pi 4 Model B, where the code used to predict the sign is also run. After successful identification of the gesture signed by the deaf person, the predicted letter is converted into its audio version that is displayed on an attached Bluetooth-connected speaker. Breaking down the software for this part of the project, the first used code is the one used for generating the dataset. Once it's run, it records all the sensor values in real time. The features recorded in this step are 5 features for the flex sensors on each finger, 3 features for the accelerometer placed on the back of the hand, and 2 features for the attached 2 touch sensors. The generated dataset is composed of 100 iterations of the readings for 10 different people, meaning that every letter in the dataset is recorded 1,000 times. After cleaning the data, a normalization process is performed on the data of the flex sensors and the accelerometer features to rescale its range from 0 to 1. The second code used is the one used for constructing and training the neural network to the final dataset. We have divided our dataset based on a 60-20-20 basis, so 60% of the dataset is used for training, 20% for validation, and 20% for testing the performance of the neural network. The third used code is the one used for predicting in real time. It generates a dataset of 100 iterations for the sign gesture and applies the neural network weights on it to determine the letter. Afterwards, the text-to-speech portion of the code sends out the audio version of the letter to the speaker.
The second part of the project is a 3D printed human-like arm that is responsible for converting spoken Arabic back into sign language on the 5 fingers of the arm using 6 servo motors and wire-controlled joints.
The 3D printed parts of the arm are assembled according to the design instructions. Wire for controlling the joints are passed through specific holes in the parts design and tied to pulleys attached to the servo motors of the fingers. The movement of the servo motors in either direction controls the pulling of the wires in the directions that flex and extend the fingers. The generated dataset in this section was based on trial and error for the values of the servomotor angles and the corresponding positions of the fingers. The process here starts with the voice recognition algorithm that works on the input speech coming from the microphone. After the speech is recognized, a text from the Arabic letter is sent to the generated dataset to trigger a set of angles for each of the 6 servomotors to represent the sign language equivalent to the spoken letter. These angles are then sent from the Raspberry Pi to an Arduino board that serves as a median that operates these servomotors. The currently available hearing aids, used to give people with hearing disabilities some semblance of the life they can fully enjoy, have crucial limitations. They only work on the basis of amplifying the sound arriving for the brain to decipher, but it doesn't translate what the ear is saying in brain language, which is required for moderate and severe cases of hearing loss, where the pattern of the neural activity is distorted to a point where the brain no longer recognizes the sound.
Our project proposes an approach that doesn't depend on the neural activity of the brain, which is considered a more complex rate.
You may have noticed that our project is working on only the letters of the Arabic alphabet. Our project is the demonstration of our approach through an MVP, or a minimum viable product. The Arabic Sign Language is composed of words and expressions that require the motion of both hands as well as the processing of dynamic variables, which is considered much more complex.
Moving forward, the project requires more experts in the artificial intelligence field of neural networks and sign language experts in order to build a final product of 2 gloves and 2 human-like arms supported with 2 forearms to be able to fully represent the entire Arabic Sign Language.
With suitable funding and expertise, a final product can be developed to benefit the deaf, dumb, as well as the deafblind through proper marketing and customer service. Our project can become a breakthrough in the world of assistive technology.
And finally, providing individuals with an equal voice and communication abilities assures our start at the same step. Thank you for your consideration.